In this video, I will show a demonstration of a performance evaluation of a distributed delegation in edge computing using Mininet. This is the outline of the demonstration, which consists of a short introduction followed by two demonstration parts. Let's start with the introduction. First of all, what is edge computing? We all know about the user devices such as mobile phones connecting to the remote clouds for all kinds of computation. Edge computing means adding an intermediate tier between the clients and the cloud. This intermediate tier resides into the access networks or the core network of the mobile network operator. And it offers computation, storage, and all other services which we usually find in the cloud, but they are closer to the user, which typically means they have less latency and they require less traffic between the edge tier and the cloud. What is computation delegation? It is when an application that resides into a user device outsources some tasks to a remote server. So for instance, if a mobile phone delegates transcoding of a video that has been captured by the user to a remote server so that it avoids running the transcoding itself. So why the application should do that? One reason is to save battery. If the device is energy constrained, then running the task on another device may save battery. Or the device may be not very powerful, which means that running the computation takes a lot of time, and in any case less than it takes if the computation is run on a remote server, which is more powerful or has a dedicated engine. Finally, the device might be such that it cannot run computation at all. In this case, it is not a matter of efficiency, either response time or energy efficiency, but rather the only option for the device to run computations is to delegate it to some outsider. What is Mininet? Mininet is a network virtualization environment. It means that it is able to create virtual network devices that live in separate Linux namespaces, so they don't see each other, basically. So what you have with Mininet is that you can create nodes and links and have real applications running on nodes, and they exchange IP packets using the links as if they were physical links. There are a lot of online resources for Mininet, since it is a rather mature software which has been defined within academia, but it is used today also in the industry. So you can you have a few links to Mininet if you don't know it and you would like to know more about it. For instance, in this demonstration, I have configured Mininet in order to emulate 18 switches, which are shown in the slide, that are arranged with a core ring and consisting of 6 nodes, and each ring node has 2 leaves. There are also a number of hosts which are not shown in the picture. The only host that is shown is the host NAT0, which is a special host because it connects to an external device, which is not part of the network virtualization done in Mininet. In fact, Mininet is not a simulator, it's an emulator, so it is able to receive and process traffic in real time coming from external devices. And this concludes the introduction of this video. We now move to the first part of the actual demonstration, in which we will show how delegation to a single edge node works. Let's start with the local execution of the application in order to show what this toy example application does beforehand. So now I will start a local computer that is able to run object detection in a picture, more specifically face detection and eye detection. I have a selfie I took a few minutes ago of myself, and I will run locally the face recognition. As you can see, the algorithm has detected correctly my face and the eyes. The specific algorithm used is not very important at this point. So I will just close the window now and run in a loop, for instance, the face recognition. We can see that the local application for face and eyes recognition is running, and we have a response time of about 550 milliseconds. Let me stop everything, and let's move to using Mininet. In our Mininet, we have all nodes from 1 to 6 that in the middle ring that are able to execute object recognition on pictures. For now, we will just use one client on my computer, which is NAT0, that connects to one single server, which is S1, the closest one. In order to do this, we have to start Mininet. Now, Mininet is setting up the topology shown. It is creating all the flow tables on the open switches in the topology. It is running a few consistency checks. So we just have to wait a few more seconds to go. And here we go. In order for my computer to access the visualized devices inside Mininet, I create an SSH tunnel. So now, when I run again the same application that connects to a server in order to have face and eyes detection, I just change the port because this port has been mapped in such a way that it connects to the visualized device inside Mininet. As you can see, the local face recognition is not running here. And after an initial delay, which is a bit bigger because it also contains the setup procedure for the SSH tunnel, we can see that face recognition is actually working. And we have one face and two eyes detection, which is correct, in a bit above 400 milliseconds, which is a bit a smaller value than 550 that we had locally, which simply means that the computer that is running face and eyes detection in the Mininet is faster than my local computer. But that's not really the point right now. If we go to the Mininet, we can also monitor the emulated resources. So for instance, in the bottom graph, we can see that the throughput, overall throughput in the network is around 8 megabits per second, which is for sending the picture to the computer S1 and for getting back the response, basically. And on the top graph, we can see the utilization of the physical CPU. We have 6 lines because there are 6 applications running face and eyes detection on nodes from 1 to 6, as I said before. But only one is being used. So the red curve, which is the bottom one, is closest to 1, while all the others are to 0. So far, everything is fine. We have one client, one server, and we're doing great. But what happens if more clients connect to the same edge node? This is something that in a real environment can happen. So to simulate this, I've prepared a script that simply starts 5 more background processes doing the same as it is being done on the top right window. In this case, what happens is that the latency that we experience becomes much greater because there is contention on the physical CPU that is running the object detection. And in fact, before it was closer to, the utilization was closer to 1, but right now is exactly 1 because the CPU is almost always busy doing object detection, but this is not enough since the user is perceiving a worse quality of experience because of contention, while there are other nodes in the network that may be able to serve better the clients during the requests. And we will show this in the second part of the demonstration. We now move to the second part of the actual demonstration, in which we will show how distributed delegation works. So in this case, what we want is to have one physical device, which is not 0, connected to Mininet, but we want to use all the processing power that is distributed over 6 virtualized nodes in Mininet. To do this, we first start Mininet as we did before. We wait for the topology to create, for the OpenFlow tables to be filled, for all the commands to be started, and for a few consistency checks again. We only change the tunnel right now so that we connect to a special device called Edge Router, which is able to do this distributed delegation. This starts the tunnel so that we can feed real packets from my computer into the Mininet network running on a remote computer. We run the same command here. And what we see, if we look to the same graphs as before, is that we have an increased network throughput because now the distributed algorithm is distributing computation among the S1 to S6 nodes in Mininet, and in fact all of them are loaded. We are not overloaded because right now there is a single client, but if we add multiple clients as I did before, now we have 6 clients in total, all on the same computer, all going through the same ingress edge router in Mininet, but which increases, by the way, the network throughput quite a lot. And as you can see, we have a utilization which is close to 1 on 6 CPU cores. And in fact, the latency for face and eyes detection is very close to what we had when we had a single server with a single client, which is exactly what we wanted in the first place. Now, you might say, that's fine, but the performance evaluation so far requires human intervention because you have to start SSH tunnels, you have to start applications on a remote host. That's not very convenient if you want to have repeatable and automated experiments. That's right. And in fact, we now conclude with the final part of the demonstration by showing how we can run a fully automated performance evaluation by using all 6 nodes from 1 to 6 that serve requests from all the other switches in a fully automated manner. So let's go back to Mininet. We can close these graphs there. We close the previous emulation session and we start, for instance, with a duration of 30 seconds. This command will now set up the network topologies as we have seen before. We'll start all the computers able to run face and eyes recognition, and we'll also start for 30 seconds the clients that are requesting face recognition by sending an image, which in this case is always the same image.jpg. And if we monitor in real time, we can see that the same graphs as before are running. We have the network throughput, which is around 40 megabits per second, and we have the utilization of all 6 CPUs being used that are moving, and they are not close to 1 because the actual rate of requests on the clients has been configured so that they do not saturate the CPU capacity. And now this experiment has ended after 30 seconds of client traffic, and in fact we also find a number of results here. These out.something files contain the latency experienced by a given client. As you can see, the age number that is appended at the end of the file indicates the ID of the switch to which clients were connecting. We can see a timestamp with a latency in milliseconds, and we can also plot, for instance, the cumulative distribution function of the latency over all the clients. The latency is on the x-axis, while on the y-axis we have the cumulative probability. So to conclude, what are the takeaways? 1. The distributed delegation enables scalability within an edge domain. This is very important. And also Mininet is a tool that enables performance evaluation of edge computing in conditions that are both controlled and repeatable. Additionally, you can also use real applications, and you can also have real devices even external to the host running the Mininet emulation. And this concludes the demonstration.